Welcome back, everybody. In this video segment, we will take a look at one section, section 2.8. This section follows in my lectures after section 2.6. And if that seems a little strange, it won't in about 3 minutes or so. I want to give you a little bit of a review of what we covered in section 2.6. In section 2.6, we looked at sketching the graphs of trig functions of the form y equals a sine omega x and y equals a cosine omega x. And what we left off with those two trig functions is that we have, associated with both of them, we have this thing called an amplitude. The amplitude is not a. That's a common mistake on exam. An exam is for students to say that the a corresponds to amplitude. The absolute value of a is the amplitude. The period of the trig function, is 2 pi over that omega, that thing that looks like a W but is really a Greek letter omega. But it's provided that omega is greater than 0, and most often omega is provided to be greater than 0. If it's not, we use the even and odd properties to get that negative out of there. Okay, let's take a look at a specific review example. Yeah, let's do that. Let's take a look at an example to review. So specific example might be sketch, let's say, exactly one period of y equals -1/3 cosine of 2/3 x. Okay, now just to remind you, on your homework, or rather in the back of your book, with the where the homework answers are located, your author doesn't sketch exactly one period or exactly two periods. He sketches maybe a period and a half or 2.5 periods. On your exams, I'm going to be very, very specific about whether how much of the graph I want to see. Very typically, I'll say sketch exactly one period or exactly 2 periods, and if I do, I want you to sketch only that number of periods and not more and not less. You're going to be graded partially on whether you know what a period is. So be careful with that. And in fact, you can use the graphs that I produce in the videos, in these video segments, as kind of an example of, or a sample of how you would produce graphs on your test. And I think you should do that on your homework too. When you're graphing on your homework, sketch either one period or 2 periods, or maybe alternate between 1 and 2 periods for the problems as they come along. Okay, so let's take a look at graphing this function. The amplitude, again, this is just a quick review of section 2.6. The amplitude is the absolute value of -1/3, which is 1/3. The period is 2 pi over omega. Omega is the coefficient of x within the trig function, so it's 2 pi over 2/3, or 2 pi over 1 times, and then we invert and multiply by 3/2, and this gives us 3 pi. Okay, and here's the graph of the function. Here's our way to getting the graph. So what I'd like you to do is first, of course, draw the axes. And here's the y-axis. Oops, I'd like to have a less crooked y-axis. So here's the y-axis. That's a little better. Okay. The amplitude is 1/3. So on your graph, pick a place along the y-axis that you want to call the amplitude. Let's call this 1/3. So we mark off 1/3 and -1/3. And then to graph the function, mark off the period. Mark off the period. The period is 3 pi, so we're going to choose to call this 3 pi. And then what I would like is the starting point for one period and the ending point for one period and 3 points in between. Okay, so the starting point is 0 for this section. When we take a look at section 2.8 in a few minutes, our starting point's going to move around either to the right or to the left. We'll cross that bridge in a minute. So I want to mark off some other points. I want to, in particular, I want to mark off the midpoint of one period. So we take 1/2 of 3 pi, which would be 3 pi over 2. Then we take half of that. Half of 3 pi over 2 would be 3 pi over 4. Just multiply 3 pi over 2 by 1/2. And the trickiest part for students tends to be that 3/4 mark. It's not that bad. If you notice that each of these points is 3 pi over 4 apart from one, they're 3 pi over 4 apart from one another. So in other words, the first point is 0. The next point is 3 pi over 4. The next point is 3 pi over 4 times 2, or 3 pi over 4 plus 3 pi over 4, which would be 6 pi over 4. So that 3 pi over 2 can be thought of as 3 pi over 4 plus another 3 pi over 4, which is 6 pi over 4, which of course reduces to 3 pi over 2. Then the next term after that, or the next point after that, then should correspond to 3 pi over 4 plus 3 pi over 4 plus another 3 pi over 4. Or wherever we left off, 6 pi over 4 plus another 3 pi over 4, which is 9 pi over 4. So that 3/4 mark in the period is 9 pi over 4. And you can make sure that you've done everything okay by adding another 3 pi over 4 to that. Oops, another 3 pi over 4 to that. You get 9 pi over 4 plus 3 pi over 4 is 12 pi over 4, which is 3 pi, and that is exactly what our period says that should be. Okay, we'll be seeing a little more practice of how to do this. It tends to be the hardest part of graphing, is getting those points in between. So I'm going to make those points disappear. You can always replay the video and get those points again, or you could go back and freeze the video if you want to take a longer look. At this point, what I like to do, and this is purely optional for you, what I like to do is I like to draw a little box around my graph. I'm not an artist. In fact, the opposite. I think I've said that more than a couple times. I don't draw very well at all. So I need little boxes to keep my graphs contained. So for each period, I like to draw 4 little boxes for each period that I draw. Now, when you're graphing sines and cosines, there are only 4 possible graphs you can get. Okay, once again, we're just reviewing section 2.6. The possible graphs are a right side up cosine, a positive cosine, an upside down cosine, a negative cosine, a right side up sine for one period, and an upside down sine. So plus sine and minus sine. So how do we know what graph we're going to get? Well, look at our original function. Look at our original function. Our original function was -1/3 cosine 2/3 x. That is an upside down, because of the minus, cosine. So we know what our graph is going to look like. We know that our graph is going to look exactly like the upside down cosine. And all we have to do is fit that into this box with 4 compartments. So the hardest part is getting all those points marked off, and I want them all. I want a total of 5 points along the x-axis for each period, and 2 points in the y direction, the negative and the positive of the amplitude. Then just graph the graph. It's an upside down cosine. So we get something like this. Oops, let's see if I can do the other half of this period more nicely. Oops. Told you I'm not an artist here. Turning out so squiggly. I think I've had too much coffee this evening. I'm going to still try one more time. Now that's okay. That'll work. And this is what I would expect you to graph on an exam if I sketch exactly one period. If I wanted 2 periods, you would sketch an exact copy of this, and it would go from 3 pi to where? Where would it end? Well, the period is 3 pi. It would go from 3 pi where we left off to 6 pi, and then I would want 3 more points in between that. You'll see some examples in a few minutes of more of these graphs. So if that didn't make sense, just stay tuned. Okay, so what we left off to finish with in that section was what I reviewed a few seconds ago, is that the general case for a sine omega x and a cosine omega x, the amplitude is always the absolute value of that coefficient of sine and cosine. And a period is 2 pi over omega, provided omega is positive. All right, so now on to section 2.8. Section 2.8. So here's our title again. It looks like a very fancy title, but there's really not much fancy going on. 2.8 is entitled Phase Shift and Sinusoidal Curve Fitting. First of all, phase shift. We in the last section we looked at transformations of the basic sine and cosine graph by increasing or decreasing the amplitude, or increasing and decreasing the size of the period. We changed the graphs from the basic graph of the sine to a graph with a larger amplitude, or a smaller amplitude, or an even smaller amplitude. Looks like about the same. Or an even smaller amplitude. Or we changed the period. We changed the period. We made the period smaller. That doesn't look much smaller. We made the period smaller. So if this is one period of the sine, then maybe we squeezed one period into a shorter area, or we increased the period, and that was a result of changing the omega in the a omega or a excuse me, the a sine omega x or b cosine omega or a cosine omega x, and the first was the change in the actual amplitude was by changing a. Okay, now we need to do one more transformation, and then we can have a lot of graphs. It'll accommodate a lot of graphs that occur in STEM field courses. We want to, besides changing the amplitude and the period, we want to be able to shift the graphs to the right or to the left. If we shift a graph to the right or to the left, what we've introduced is something called a phase shift. Hence in 2.8 we have this thing called phase shift. The second part of the name of the section, sinusoidal curve fitting, basically means we're still graphing sines and cosine functions. They tend to be the most important graphs of all 6 of the trig functions in the sciences. They tend to be the most important. And why not then sinusoidal and something like cosinusoidal? Why just mention the sine function? Well, we only mention the sine function in sinusoidal curve fitting because cosine and sine are exactly the same graph. We talked about that in the last section. They're just shifted over from one another. The sine and cosine are exactly the same shape, and I gave you a detailed explanation of that. If this is the sine function, then the cosine function looks like this. They are identical in shape. They're identical in shape. So in a sense, they're both really just a sine function. So in this section, we really look at one additional feature of the graph, and that is to change or to shift the graph to the right and to the left. Additionally, though, what I like to introduce in this section is an introduction to using the graphing calculator to sketch the graph of trig functions. So we'll do that at the very, very end. So let's start with a graph that contains some sort of phase shift, a shift to the right or to the left. So for example, let me start over here. So for example, sketch, let's say exactly one period. Exactly one period of y equals cosine of x minus pi over 2. Okay. Now you notice the very first thing here is that there's a change in our equation that did not occur in section 2.6. In 2.6 we changed, if this is the cosine function, we changed the coefficient a to alter the amplitude, or to flip the graph upside down or reflect the graph. We also changed the period by changing omega. The period wasn't omega, the period's 2 pi over omega, but if we change omega, we change the period. Ours has something different. We have y equals cosine of x minus pi over 2. So there's really a 1 as a coefficient of the cosine, so the amplitude is the absolute value of that 1, which is 1. And we still have a 1 as a coefficient of x, so the period is 2 pi over that. That's our omega, which is 2 pi. So we haven't changed the amplitude or period of the regular cosine function. We have a different change here. Now, there's a technique that I use to graph these. It's a little different from the technique in your textbook. I think your author might hit on it, but he doesn't emphasize this technique. And I want you to become familiar with this technique. It's really very simple. Okay, so I want you to notice something about the graph of the basic cosine function without any kind of amplitude or period change, without any amplitude or period or phase shift change. So here's a graph, a basic graph of one period of y equals cosine x. And I want you to follow along with me on this. One period, when again we're looking at y equals just plain old cosine x. One period starts when and one period ends when. One period starts when x equals 0, and one period ends when x equals 2 pi. That's extremely clear. I know you see that. One period starts when x equals 0, and one period ends when x equals 2 pi. Okay, so one period starts when I place x equals 0 into the angle. One period ends when I place 2 pi into the angle of the function. Okay, so our function now doesn't have x as the angle. Now y equals cosine of x minus pi over 2. So now one period starts when we don't have x as the angle anymore. We took out x and put x minus pi over 2. So one period starts when x minus pi over 2 equals 0. And one period ends when x minus pi over 2 equals 2 pi. Okay, so let's see what that amounts to for x values, our actual starting points for x. We need to solve both of these equations with a little bit of algebra for x, and then we move on. So if I add pi over 2 to both sides of the first equation, I get a new starting point. The graph doesn't start at 0 anymore. This graph starts when x equals pi over 2. Also, the graph ends at a different place. Now, to solve this second equation, I'm going to use a little bit of a trick from algebra. I'm going to multiply both sides by 2. It clears the denominators. Now, you don't have to do that. If you don't mind dealing with fractions, you can solve for x by leaving the pi over 2 in. But if you multiply both sides by 2, you get 2x minus pi. If you distribute the 2 on the left, equals 4 pi. So 2x equals 5 pi. Divide both sides by 2. X equals 5 pi over 2. Okay, now check out what that does to the graph of our function. It's going to have a really profound change on the graph of our function. Before our graph started when x was equal to 0. When x was equal to 0, and then ended when x was equal to 2 pi. Now our graph starts when x equals pi over 2. Good grief, I can't get my surface to cooperate here. When x equals pi over 2, and ends when x equals 5 pi over 2. I've shifted my graph to the right by pi over 2. Okay, to finish seeing that's true, or to really emphasize that that's true, let's do what I suggested that you do when you graph on your homework and on a test. I have the new starting point, I have the new ending point, and I want 3 points in between. I want 3 points in between. For every period, I want a starting point, an end point, ending point, and 3 points in between. And I'm going to know what those numbers are. Okay. Now, this is the tricky part for some students, and it's really not that difficult. It's really not that difficult. I'm going to show you a little example in green of a simpler one. Suppose I start at 1 and I end at 5. So I want 3 points in between. It's pretty clear that those points need to be 2, 3, and 4. Okay, but suppose we didn't know that. If you want the point exactly between 1 and 5, you can get that point by averaging 1 and 5. Or in other words, if you want the point between 2 points, you take the first point, add the second point, and then divide by 2. So that point must be 3. And then you repeat the process. For the other 2 points. I want the midpoint between 1 and 3. That's 1 plus 3 divided by 2. Or 4 over 2, which is 2. You actually did this in Algebra 2, or in intermediate algebra. You may not remember it quite this way. You found the midpoint. You get the midpoint of 2 x values. You take the 2 x values and add them up, x1 plus x2, and then divide by 2. That occurred in intermediate algebra when you were graphing midpoints. So if I want the point between 3 and 5, it's 3 plus 5 divided by 2. Which is 8 divided by 2, and that's equal to 4. So this is the go-to way to get the 3 points in between if you can't see what the points should be. If you can see that the points should be what the points should be, you mark off the points. Okay, but a lot of students have a hard time doing that. Okay, so suppose I want the midpoint. Suppose I want that point right there. To get that point right there, I take pi over 2, first point, plus the last point, by pi over 2, and then I divide by 2. So 1 pi over 2 plus 5 pi over 2 is 6 pi over 2, and then I divide by 2. Well, 6 pi over 2 is 3 pi, and then divide by 2. So that must be 3 pi over 2. That must be 3 pi over 2. Pi over 2. So do the same thing. Do the same thing to find. Let me make a little room here. Let me get rid of the green. So we're going to do exactly the same thing with the point between 1 pi over 2 and 3 pi over 2. So between 1 pi over 2 and 3 pi over 2, you take 1 pi over 2, oops, here, 1 pi over 2 plus 3 pi over 2 and divide by 2. 1 pi over 2 plus 3 pi over 2 is 4 pi over 2. It's just fractions. 1 plus 3 is 4 over 2. 4 pi over 2 is 2 pi. Divided by 2 is pi. Okay. Now that third point, excuse me, to get that third point, you can get a little tricky to get it right away. That pi that I just put there, you could write as 2 pi over 2, and there's a pattern there. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, and then 5 pi over 2, of course, to end things up. Now, you don't have to use that trick. Suppose we don't see that trick, or suppose we don't want to use that trick. To get the point exactly between 3 pi over 2 and 5 pi over 2, you take 3 pi over 2, the point on the left, plus the point on the right, and divide by 2. Okay, so you got 3 pi over 2 plus 5 pi over 2 is 8 pi over 2. Then divide by 2. 8 pi over 2 is 4 pi. Divide by 2. 4 pi over 2 is 2 pi. And this needs to happen every time you have a phase shift, every time you shift a graph to the right or to the left. And so you see a starting point, an ending point, and 3 points in between. Total of 5 points per period. So the amplitude is 1. Remember, the coefficient of this cosine function was 1. So I'm going to draw my little box, but the little box is not going to include the x-axis or the y-axis this time, because our new starting point is away from the y-axis. And if you don't want to draw the box at all, that's fine. If you can keep your graphs contained without drawing a little box, fine, more power to you. Seriously, that makes you a good grapher. Okay, so we're graphing is it upside down or right side up? It is a right side up cosine since it's positive cosine. We memorize the shape of the cosine. It starts at 1, goes down to -1, comes back up to 0, and then goes back up to +1. And this is what I would like to see. And you don't have to be too fancy. You notice my graphs are not at all fancy, but they tend to get the job done. Okay, and that's all you have to be able to do, is just get the job done, get the basic shape of the sine or cosine. The big thing, the important thing, well, the basic shape's important, but next to the basic shape is the points along the x-axis and the points along the y-axis. Okay, and on your exam, I'm going to be very explicit about wanting 1 period or 2 periods or whatever, and you give those 1 or 2 periods exactly. Don't draw extra, don't draw not enough. Draw exactly 1 or 2 periods, or however many periods I request, and those points, the points for the amplitude and the 5 points along the x-axis per period. Okay, let's do another one. Let's do one, a little more elaborate one. So let's say example. And I want to pick a decent example here. So, okay, so let's say I want to sketch exactly 2 periods of y equals -3 sine 2x minus pi over 2. Okay. What we're doing here is actually quite amazing. You should be impressed with yourself when you get this stuff. These are complicated graphs. These are extremely complicated graphs to get. What makes them not so difficult for us is we know the basic shapes of sines and cosines, but you could not use the technique that you used in intermediate algebra or algebra 2. By that I mean you couldn't at all construct a chart of x's and y's and then connect the dots very effectively to get this graph without knowing, of course, what the shape of the sine and cosine were. So what you're doing here is really some heavy-duty graphing. Okay, so we can identify some stuff. We can identify the amplitude is the absolute value of -3, +3. The period is still 2 pi over the omega. Omega is the coefficient of x, as long as that coefficient's positive. Now we have something called a phase shift. I've been mentioning the phase shift without giving it a quantity, identifying the quantity. So I'm going back to the previous problem, and I'm going to insert in red or purple here. For this graph that we just did, and I'm going to squeeze down there we go. For this graph that we just did, we have something called a phase shift. The phase shift is the new starting point for the graph. The phase shift in this case is pi over 2. Okay, the phase shift is pi over 2. That pi over 2 amounts to the new starting point on the graph. So that's why we call it, and of course I went to red there, that's why we call it the phase shift, okay? Now, I want to put a bug in your ear here. We know from our work last time that amplitude and period are always what kinds of numbers? They're always non-negative numbers. Amplitude and period are never negative. So I want you to think about something, and we'll get back to the answer in a little bit. But can phase shift be negative? Can phase shift be negative? Phase shift is the new starting point. Well, think about that. Of course, I'll give you the answer in not too long. Okay. So back to our graph. Our graph is exactly 2 periods of -3 sine 2x minus pi over 2. Okay. All right. So let's see here. Let me make sure I'm on track here. Okay. In fact, I'm gonna make one little change on our graph, or our function. This is sort of an impromptu change. See that minus that was there? That minus, change that to a plus. Change to plus. This is a good idea for us. Okay. Okay, so change that to a plus. Okay, this is all right. So let's do it. Nothing changes so far. So I'm going to use exactly what I did last time in the last problem. 1 period. Oh, actually, I asked for 2 periods in this one, didn't I? So, okay. 2 periods. 2 periods. 2 periods. Start when and end when. 2 periods are going to start when and end when. When? Okay, two periods start when, well, what's the angle? It's 2x minus 2x plus pi over 2. So 2x plus pi over 2 equals 0. Okay, and do the same thing I did in the previous example. That same two periods, the two periods are going to end when, well, if it was one period, I would end the graph when the angle's 2 pi. Okay, but it's not one period. It's two periods. So I set the angle 2x plus pi over 2 equal to 4 pi. So if you want to graph one period, set the angle equal to 0, then set the angle equal to 2 pi, and then solve for the new x values. So starting and ending point. If you want two periods, start at 0, start when the angle equals 0, and then end when the angle is 4 pi. If I wanted three periods, you start when the angle is 0, and you end when the angle is 6 pi. So every period of sine and cosine is going to have an ending point. 2 pi. Well, I think that sentence isn't going to work out. One period ends with 2 pi. Two periods 4 pi. Three periods 6 pi. Four periods 8 pi, etc., etc., etc. Okay, so I'm going to get rid of that 2 pi and put that 4 pi in there. All right, so let's solve for x. So I'm going to subtract pi over 2 from both sides in the first equation. So 2x equals negative pi over 2. And in the second equation, I'm going to do that little trick that I suggested. I'm going to use some algebra, basic algebra. I'm going to multiply both sides by 2 to get rid of the fractions. So I'm going to get 4x if I distribute the 2 on the left. 4x plus 2 times pi over 2 is pi equals 8 pi. So 4x equals 7 pi. So x equals 7 pi over 4. Okay. So let's graph this thing. Okay, we got a ways to go, but we have all we need to get a really good start on this. I'm going to graph the axes first. So here's our x-axis. Here's a decent y-axis. And we have a starting point of negative pi over 2. So I'm going to put that right here. Negative pi over 2. Okay, I stopped the video and noticed that I didn't finish with the start point. I subtracted pi over 2 from both sides, and then I forgot to divide both sides by 2. That was a little bit of a blunder on my part there. Okay, so we have a starting point of negative pi over 4. Negative pi over 4. And we have an ending point of 7 pi over 4. Okay, now I put that ending point way along the x-axis. Why did I do that? What's going to be between those 2 points? How many periods? 2 periods. So I'm just making enough room. Now I have a lot of points to find. So for each period, you need 5 points. So for each period, you need 5 points. Let me give you an idea of what I'm talking about. 1, 2, 3, 4, 5 points. So if it was a sine, I would need 5 points to get the sine. That's one period. So I have 1, 2, 3, 4, 5. So how many more points am I going to need for a second period? And the answer isn't 5, because the next period is going to start with the 5th point. So I'm going to need a total of 9 points to get a complete period. So 5, 6, 7, 8, 9. Again, because that point in the middle, number 5 for the first period, is the starting point for the next. So the reason I say that we need 9 points is that I wanted to justify my putting 7 pi over 4 so far on the right. Okay, so let me get rid of this graph. We don't need this. This erasing is sort of like my erasing on the whiteboard, so I justify it. This is going to be our best classroom setting. There's going to be some erasing done. All right. So I need 9 points total. So I need a lot of points. So let's find the midpoint. To find the midpoint, we take negative pi over 4 and then add 7 pi over 4 and then divide by 2. Negative pi over 4 plus 7 pi over 4 is 6 pi over 4. Then divide by 2. So this is 6 pi over 4 divided by 2. So that's like 6 pi over 4. If I invert and multiply, it's times 1/2. That's 3 pi over 4. Okay, so the point exactly between negative 1 pi over 4 and 7 pi over 4 is 3 pi over 4. I got to keep doing this. 2 periods have to go in this area. So I need some more points. So let's find the midpoint between negative pi over 4 and 3 pi over 4. So negative pi over 4 plus 3 pi over 4. Add the two extremes, left and endpoints and right endpoints, and then divide by 2. Always, you can always do this. Sometimes you don't have to. Sometimes you can see what the answer is going to be. So this is 2 pi over 4 divided by 2, or 2 pi over 4 times 1/2, which is 1 pi over 4. So this is 1 pi over 4. So I need to keep going with this. So what's the point exactly between negative 1 pi over 4 and positive 1 pi over 4? This one's easy. It's 0. It's 0. Negative, if you want to use the adding the left and adding the right and dividing by 2, go right ahead, but you don't really have to. The point exactly between a negative quantity and its opposite is 0. Okay. So let's continue. So I need the point exactly between between 1 pi over 4 and 3 pi over 4. So I'm going to have 1 pi over 4. Let's do that next. 1 pi over 4 plus 3 pi over 4, then divide by 2. Always add up the left and right, divide by 2. 1 pi over 4 plus 3 pi over 4 is 4 pi over 4. And divide by 2. Well, 4 pi over 4 is pi, so this is just pi over 2. Okay, I'm going to scoot 3 pi over 4 over a little bit. And just adjusting for midpoints. So here's 3 pi, here's pi over 2. Well, there's some bad news. We have to find, there's where the first period's going to go. Between negative 1 pi over 4 and 3 pi over 4. That's our first period. The second one's got to go between 3 pi over 4 and 7 pi over 4. I'm going to move 7 pi over 4 over a little bit. So we have the same amount of room. Now, we don't really need to go through that averaging business to get these other midpoints. And let me show you why. Oops. Let me show you why without erasing everything. Let's see. I need 3 more points. Okay, it's not difficult to see them. If we make that pi over 2 right there have a denominator 4, then we can see what the next points should be. Look at the points. Negative 1 pi over 4. Then bounce to 0. Negative 1 pi over 4 plus pi over 4 is 0. 0 plus pi over 4 is 1 pi over 4, plus another pi over 4 is 2 pi over 4, 3 pi over, there's a pattern. We have 1 pi over 4, 2 pi over 4, 3 pi over 4. So the next one should be 4 pi over 4. I'll write it here. 4 pi over 4. Then the next one should be 5 pi over 4. Next one should be 5 pi over 4. Then the next one should be 6 pi over 4. I'm putting those below because they can be reduced. And the last one should be 7 pi over 4. So at some point, you can stop using the method of averaging left and right endpoints to find corresponding points and just look for a pattern. Okay? If you don't see a pattern, then just continue to average until you get the total of 9 points for 2 periods. 9 points are necessary for 2 periods. And we should have 9 points here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. Okay. Okay. So when we have those 9 points, basically it's over. Our graph, or our function, rather, is an upside down sine function. The negative tells us that it's an upside down sine function. So we expect our graph of 1 period to look like an upside down sine. So is our graph going to look like that red graph? No, that's 1 period. Our graph's going to look like that twice. Okay, we have 1 period and we have 2 periods. 2 periods. Okay, so we know what the shape is going to be. All we got to do is, well, I like the little box business to keep my graphs contained. What was the amplitude of this thing? 3. Again, that's optional. So here's 1, 2, 3, 1, 2, 3, and let's draw a little box. Big box in this case. In this big box, we are going to squeeze 2 periods. Okay. So each period has 4 compartments. 1, 2, 3, 4 compartments. So there's our first period. 1, 2, 3, 4 compartments. An upside down sine graph in there. I'll draw for 1 period at a time. So it's going to look like down, up, down. There's 1 period. Again, if you don't need the little boxes, don't draw the boxes in. It's totally up to you. Experiment. See if you're good enough at graphing this stuff without having to draw little boxes to keep stuff in. Here's our second period. The accuracy here is tremendous. These graphs would be very, very difficult, if not impossible, to graph them without using some sort of technique, memorizing the shape, memorizing a shape with finding some points between periods and stuff. These are very complicated graphs. Okay. So before we dig into the use of the calculator to do this, let's summarize. Summary. Well, part of that summary is going to involve phase shift. So what's the phase shift for this graph? What's the phase shift? Phase shift. And remember the question I posed that we never answered? I said that the quantities amplitude and period are never negative. Never. Amplitude and period are never negative. And then I asked you the question, I asked you to think about the question, can phase shift be negative? Where does this graph start? It starts at negative pi over 4. That is our phase shift. The phase shift can, in fact, be negative. Phase shift can be negative. Amplitude and period are never negative. Phase shift can be negative. Okay. So here's the general case. Y, it's either going to be a sine or a cosine, so y is going to equal a sine omega x, but then minus phi, or y equals a sine omega x, oops, sine again, no, cosine, a cosine omega x minus phi. Two of the things we already know, or two of the things are from before. The amplitude is equal to the absolute value of A. The period is 2 pi over the omega, provided the omega is positive. And there were a couple homework problems that you did where you had, I think it was at least two, where you had to deal with that omega negative. So what's the phase shift? The phase shift's not phi. The phase shift is not phi. Let's take a look again, not at the whole thing, but just the equation we did before. It was -3 sine 2x plus pi over 2. -3 sine 2x plus pi over 2. And we said that the phase shift was negative pi over 4. That phase shift is the new starting point for the graph. You get the phase shift by setting the angle equal to 0. To get phase shift, set the angle, in this case 2x plus pi over 2 equal to 0. The phase shift is the new starting point. This says 2x equals the negative. We already solved it. 2x equals negative pi over 4. It's right. It's the one I forgot to put the divide by 2 before. That's how you get the phase shift. So what about our general case? What about for y equals a sine omega x minus phi, or y equals a cosine omega x minus? I'm trying to find formulas, general formulas for phase shift. How do you get phase shift? You set the angle equal to 0 to get the new starting point. The phase shift is a fancy way of saying a new starting point for our graph. So set omega x equal to 0, omega x minus phi equal to 0, add phi to both sides. So x equals phi over omega. That's the phase shift. That is the formula for the phase shift. Oops. I'm trying to change the color of this thing. That is the formula for phase shift. Okay? So amplitude, absolute value of A, period, 2 pi over omega, provided omega is greater than 0, and phase shift. I'll squeeze it in here. Well, there's no need to squeeze. I can have a feature in here where I can add some more room. So add just a little bit of room. So the phase shift, which could be negative, is equal to phi over omega. Phi over omega. Now keep in mind the equation has to start, for that to be phi over omega, the equation has to start with omega x minus phi. So if just a real quick example before we go to the calculator, if I want to find the phase shift, and I have something like y equals, I'm just making this up, -2 sine 3x plus pi over 2. The phase shift is phi over omega, but in order to use that phi over omega, it needs to be omega x minus phi. So I'd have to rewrite the equation like this. So it looks like a sine omega x minus phi. So there's a better way to get the phase shift than the phi over omega, but the phase shift is phi over omega. Phase shift equals phi over omega. Phi is negative pi over 2, and then over omega 3, or if you invert and multiply, you get negative pi over 6. Easier, better, because it's confusing to keep track of that minus, just set 3x plus pi over 2 equal to 0 and solve. So 3x is going to equal negative pi over 2. X equals negative pi over 6. The same thing. Okay. You use whatever is convenient for you. If you like the formula, use the formula. If you want to just set the angle equal to 0 and solve, I think that's the best thing, but I'll leave that up to you. Okay. Let's finish up with a little bit about the graphing calculator. So let's finish up with a little bit of work with our graphing calculator. Now, before I get into the graphing calculator, something I'd like to make real clear about graphing calculators and the exam. A lot of your work, in fact, most of your work on the exam is to be done without the graphing calculator. Now, you can use your graphing calculator to verify your shapes and stuff, but on your exam, I want you to provide all that information leading up to your graphs that we talked about, those points along the x-axis and the points along the y-axis. So with that in mind, let's discuss how to use the graphing calculator to get an image of these sines and cosines. So I've drawn your calculator for you. If you happen to have a TI calculator, it will look like this. I'm familiar with the Texas Instruments calculator. It's the reason why I draw this version and not a Hewlett-Packard or Casio or other calculator. But they're all, as I understand, they're all pretty similar. Okay, so what you're seeing is an image of what happens when you access the graphing feature in your calculator. The graph goes in the screen, obviously, and what you're seeing is the view of what's called the standard viewing window, which was programmed into your calculator when it left the factory. The standard viewing window is a viewing window of a particular size. It has x ranging between -10 and +10, and y between -10 and +10. And this viewing window, the standard viewing window, we change all the time, and it can instantly be changed back just by accessing a couple of buttons on the calculator that'll turn it back. I'll show you that in a second, but just a little more terminology. If this is the standard viewing window, again, the window that your calculator left the factory in, then this x value at the very left is called x min. This x at the very right hand side is x max. Y min is the lowest y value, and y max, the very top mark, 4, 5, 6, 7, 8, 9, 10, the very top mark at 10 should be y max. Now this is called the standard viewing window, and if you push the window button, and if your calculator is in the standard viewing window, the window button is the button, the second button in from the left. I've got it drawn in for us here too. You should see the standard viewing window numbers appear. You should see x min equals -10, x max equals +10. You should also see something else. You should see x scale, SCL, and it's 1. That's the distance between the marks along the x-axis and the y-axis. Those marks are called tick marks, T-I-C-K, tick marks. So it's the distance between each tick mark. Then you see y min is -1, y max, it's -10 rather, y max is +10. Then the scaling on the y-axis, the distance between tick marks on the y-axis is 1. And you also see something called x-res, which I assume means resolution, but I have no idea what it does. Honestly, I just don't know what it does. Okay, so this is what you see, as you can leave the x-res at 1 and it won't change anything, as far as I can tell over the past 20 years of using this calculator. Okay, so this is your standard viewing window. These are the numbers corresponding to the standard viewing window, and we change these numbers depending on the function. So let's get to it. Let's sketch exactly one period. Example, sketch exactly one period of, let's say, y equals sine of x. Okay. What that means is that in my viewing window, I want to see this. I want to see in the viewing window exactly this, and nothing more and nothing less. Now that's not going to happen if you sketch this in the standard viewing window. Okay, this is what we want to see in our viewing window. So there are two steps to graphing. One, enter the function in your calculator. That's the easy part. Even the second part's not that hard. Enter the function. And two, change the viewing window, or enter the viewing window. Okay, so let's do each of these things. To enter the function, press y equals the button, the top button in the button in the top left hand corner. Press y equals. Press that button, and it's waiting for you. The calculator's waiting for you to enter the sine function, or whatever function you want to graph. You should see y1, y2, etc., etc., etc. y1 equals, y2 equals, y3 equals. I think it goes up to y7 on my calculator equals. So what you enter, and the cursor should be flashing over y1, you push the sine button, sine, and you need to enter x. Well, there's a button that's recycled for a whole bunch of different variables depending on what application you're using. It's the xt theta n button. Excuse me. Okay. And then close the parentheses. You'll see in your calculator sine, and then it'll say x with an open set of parentheses. You need to close the parentheses. So push the close parentheses button above number 9. Okay. So when you enter the trig function, the next thing to do is to enter the viewing window. Now, if you skip this step, maybe you just skip this step, and your calculator's in a standard viewing window, and you just push graph, you'll see a terrible graph. If you sketch this graph, if you use the standard viewing window, which means you use the standard the window that the calculator left the factory in, you will see a very poor graph. You'll see this. This is considered a very, very poor graph. And the reason it's so poor is that it has a whole bunch of periods, and we don't need to see more than one period of the graph, because one period is the complete shape of the graph. It just repeats itself. It has more than one period. For see, to the right of the y-axis, it looks like it has a period and a half. About to the left, another period and a half. And there's a bunch of wasted space. There's a whole bunch of wasted space. The wasted space occurs above and below where the graph occurs. So let's get rid of that and get rid of the extra space along the x-axis so we only see one period. So the second step then is to enter a viewing window. Enter a viewing window. All right. So push window. Push the window button. Window. And change some of the settings. Change X min, X max, change Y min and Y max. You can leave the scaling alone. Change the X min, X max, Y min, Y max. The X min, now we're graphing the sine function, should be 0. The X max is 2 pi. So replace X min with 0 and then press enter. Then enter 2 pi. The pi is above or right below the clear button in blue though, so you have to push second and that button, second pi, second 2 pi, or 2 times second pi. Y min is the negative of the amplitude. Y max is the positive of the amplitude. So in general, X min is the start. Let me increase the thickness of my pen here. Let's see if I did it. Okay. X min is the starting point. Start point along the x-axis. Well, X max is the end point along the x-axis. Y min is the negative or the opposite of the amplitude, and Y max is the amplitude. Now if you change those numbers and then push second graph, you should see, oh, not second graph, sorry, just graph. You push second graph, you'll get table. If you change those numbers in the window to 0 to 2 pi along the x-axis, and then -1 to 1 along the y-axis, and you push graph, you will see what we wanted to see. You will see exactly what we want to see right here. Okay, now let's end this video segment with one more graph, not a new one. We're going to go back in history. We're going to go back in history to the graph that we did before. We want to graph y equals -3 sine 2x plus pi over 2, but I want 2 periods again. So here, let me go back here. Let me do this off camera so that you don't have to see all this erasing and stuff. I'll be back in about 1 second. So here's the last problem we did by hand. Sketch exactly 2 periods of this, and I'm going to add to the directions using a graphing calculator. So graphing calculator. Okay, now there's work to do. We did the work, so we don't have to repeat it. We found that the starting point was -pi over 4, so we need that. So we have all that work to do before we even start the graphing calculator. It's not that much work. We find the end point by setting 2x plus pi over 2 equal to how much for 2 periods? We set 2x plus pi over 2 equal to 4 pi for 2 periods. And we change our viewing window. Okay, but I'm getting ahead of ourselves. So step 1, enter the function. Enter function. Enter function. And you press y equals, and you'll have y1 equals, and you can clear the sine function that we had before. And you press -3. Be careful. Careful, don't use the subtraction button for this negative. This has to be the minus or the opposite button, not the subtraction, not subtraction. Okay, so -3 or -3 times, then you push the sine button. The sine will open the parentheses, sine button will open the parentheses for you, and you push 2x plus pi divided by 2. Okay, so if you do that, that enters the function. So you have -2, I'm doing it with us to make sure that this works out, -2 times the sine of 2 times x plus, remember the x button is the one that says xt, theta, and n, 2x plus pi divided by 2, and then close the parentheses. So the calculator, you've got this thing entered into the calculator, the function entered, and then you change the viewing window. So you enter the new viewing window, enter viewing window. And the viewing window is going to have some changes. So for x min, you're going to have negative pi over 4. Negative, remember the negative button, not the subtraction button. Negative pi divided by 4. Then push enter. X max will be 7 pi. 7 pi over 4? 7 pi divide by 4. What will y min and y max be? Y min and y max. Well, we figured out that the amplitude of this thing was 3, so it'll be negative 3. Remember the negative, not the subtraction button. Positive 3 for y max. So I'm gonna enter those things. I know it takes a little time on camera, but I'm going to do it anyway. So negative pi over 4, enter. And then 7 pi over 4, enter. You could push graph if you wanted to. X scale, leave the same. Negative 3 to 3, so negative 3 to 3 along the y-axis. Okay. I forgot to mention that in the window, or rather in the mode of this, the calculator has to be in the Radian mode. And as soon as I realized I neglected to say that, some of you might be trying to get graphs and they're not showing up. If your calculator's in a degree mode, it's got to be changed into the Radian mode. I apologize. It just occurred to me. Okay. So if the mode is in the right thing, if the calculator's in the right mode, and the viewing window is correct and the function is entered correctly, you should be able to push graph and see exactly 2 periods. You should see exactly 2 periods of this upside down sine function. You should see exactly what we graphed by hand. You should see exactly, watch your eyes, I'm flipping back up here. You should see exactly what we have and what we achieved earlier. What you don't see, which requires human work, what you won't see are those 9 points along the x-axis and the 2 points along the y-axis, one at 3, one at negative 3. So that has to be done by hand. Okay, so we're done graphing sine graphs. Sine graphs were taken care of again in sections 2.6 and 2.8. So we're going to look at 2.7 in a separate video segment. It's the graph of the other 4 trig functions. And, well, we took 2.5 or 3 hours to graph different sine and cosine functions. We're only going to take 20 or 30 minutes to graph the other 4. They're not that important as the sine and cosine graphs are for STEM fields, so we don't take too much time with them. In any case, this ends this video segment. Go ahead and start homework on section 2.8 as soon as you possibly can. And as always, I am looking forward to talking with you again soon.